The insane engineering of the P-47 Thunderbolt. In 1943, American bomber crews flying over Europe faced a brutal mathematical reality. The bombers could fly at 25,000 feet. The enemy fighters could climb to meet them, but the escort fighters meant to protect them couldn't go the distance. At high altitude, engines suffocated, power dropped, drag increased, and aircraft that looked dominant at sea level became underpowered liabilities in the thin air above Germany. Here's the problem in its simplest form. Power available decreases with air density. Drag also decreases with density, but lift decreases too. So to maintain lift at altitude, you either increase speed, or increase wing area, or increase air density inside the engine. And in the early 1940s, engineers were trapped by that third constraint, because piston engines depend on oxygen. Less air density means less oxygen per combustion cycle. Less oxygen means less fuel burned. Less fuel burned means less power. And at 30,000 feet, air density drops to roughly 1/3 of sea level. So, on paper, a high-altitude escort fighter with extreme power and long range should not exist. And yet, the Republic P-47 Thunderbolt did. It was the heaviest single-engine fighter of World War II. It was not the most elegant. It was not the most aerodynamically clean. But it was devastatingly effective. Today, we're going to examine the insane engineering of the P-47 Thunderbolt through the lens of aviation engineering and aerodynamics, with a focus on thermodynamics and high-altitude performance. And more importantly, we'll ask, why did it have to look the way it did? Why was it so large? Why was it so heavy? And why did all of that make it brilliant? 1. The context, a war at altitude. Visual, archival footage of Allied bombers over Europe. In 1942 to 43, the United States Army Air Forces committed to daylight strategic bombing over Europe. The aircraft leading that charge was the B-17 Flying Fortress. It cruised at 25,000 to 30,000 feet. That altitude wasn't arbitrary. At 30,000 feet, flak accuracy drops. Fighters struggle to climb. Bombers gain defensive advantage. But escort fighters were the weak link. Aircraft like the early Supermarine Spitfire were exceptional dogfighters, but they lacked range. And high-altitude performance degraded rapidly. The problem was systemic. You needed long range, high speed, high-altitude power, heavy armament, survivability, and physics punishes you for wanting all 5. 2. The physics constraint, air is the enemy. Let's start from first principles. The lift equation. L equals backslash frac 1, 2, backslash rho v squared sc underscore, where rho equals air density, v equals velocity, s equals wing area, c underscore L equals lift coefficient. At 30,000 feet, rho drops dramatically. To maintain lift, increase velocity, increase wing area, increase lift coefficient. But increasing wing area increases drag. Increasing velocity increases drag quadratically. Drag equation. D equals backslash frac 1, 2, backslash rho v squared sc underscore d. At high speeds, parasitic drag dominates. Now add another constraint. Engine power output depends on mass airflow. Mass airflow is proportional to air density. So as altitude increases, engines produce less power, exactly when you need more. This is the high-altitude paradox. 3. The solution, turbo-supercharging. The core innovation of the Republic P-47 Thunderbolt was not its guns. It was not its ruggedness. It was its turbo-supercharger system. Visual. Exploded diagram of turbo-supercharger routing inside fuselage. Unlike mechanically driven superchargers, the P-47 used exhaust-driven turbocharging. Here's the thermodynamic logic. Exhaust gases exit the engine at high velocity and high temperature. Instead of wasting that energy, route it through a turbine. The turbine drives a compressor. The compressor increases intake air density. More oxygen, more fuel, more power. This bypasses the altitude density problem. At 30,000 feet, while other engines suffocated, The P-47's Pratt & Whitney R-2800 could still produce enormous power. But here's the catch. Turbochargers are large. They're heavy. They generate extreme heat. So where do you put it? Republic's answer was radical. They put it in the rear fuselage. 4. Why the P-47 was so big. Visual, side-by-side size comparison with a Spitfire. The P-47 was enormous for a single-engine fighter. Why? Because the turbocharger system required long ducting for exhaust, intercoolers, large compressor housing, complex airflow management. Air entered at the front. Exhaust traveled to the rear. Compressed air returned forward to the engine. This created long internal duct systems, structural reinforcement needs, increased weight. The result? An aircraft weighing over 8 tons fully loaded. That's closer to a light bomber than a fighter. And yet it worked, because high-altitude power matters more than elegance. 5. The radial engine, thermodynamics at scale. At the heart of the P-47 was the Pratt & Whitney R-2800 double wasp, a massive 18-cylinder radial engine. Visual. Cutaway of radial engine showing cylinder arrangement. Why radial? Air cooling. Liquid-cooled inline engines are aerodynamically cleaner, but they require radiators, coolant lines, vulnerable systems. Radial engines are air-cooled, are more damage-tolerant, can absorb battle damage better. From a materials science perspective, air cooling requires fins to increase surface area, precise airflow channeling. Thermal management becomes critical. Combustion temperatures exceed 2000 degrees Celsius. Cylinder heads must withstand extreme thermal cycling, all while spinning at thousands of RPM. This is mechanical engineering pushed to wartime production scale. 6. The trade-off drag. Radial engines are blunt. They increase frontal area. Increased frontal area increases parasitic drag. But here's where physics plays a trick. At very high altitude, rho is lower. Drag decreases proportionally with density. So the aerodynamic penalty of a large radial engine becomes less severe. Meanwhile, the turbocharger preserves power. So relative performance improves with altitude. This is counterintuitive. At sea level, the P-47 was not the best dogfighter. At 30,000 feet, it was lethal. 7. Structural engineering. Why it could dive. The P-47 earned a reputation for incredible dive speed. Could exceed 500 miles per hour in a dive. Visual. Structural stress visualization during high-speed dive. At high speeds, dynamic pressure increases. Q equals frac 1, 2, rho v squared. Even at lower altitude density, velocity squared dominates. Control surfaces experience extreme forces. Many aircraft of the era encountered compressibility effects near Mach 0.7 to 0.8. Shock waves formed on wings. Control reversal occurred. The P-47's mass and robust structure allowed it to survive high-speed dives better than lighter aircraft. But mass is a double-edged sword. It increases inertia, which means it doesn't turn as tightly. 8. Armament, ballistics, and energy. 8.50 caliber machine guns. That's kinetic energy on a terrifying scale. Each round carries thousands of joules. Multiply by rate of fire. Visual graph comparing projectile energy. But guns add weight. Weight increases wing loading. Wing loading affects turn rate and stall speed. The P-47 had high wing loading. This reduced low-speed maneuverability. Again, a trade-off. It was not optimized for tight-turning dogfights. It was optimized for high-speed energy fighting. Climb, dive, disengage. Energy management over agility. 9. The misconception. IT was too big. There's a popular belief that the P-47 was inferior because it was large and heavy. This misunderstands engineering intent. It was not designed to outturn a Messerschmitt Bf 109. It was designed to survive, escort bombers, operate at altitude, deliver heavy firepower, and it excelled in that role. Later in the war, with drop tanks, it gained extended range, rivaling the North American P-51 Mustang. But the Mustang was more aerodynamically efficient. So why didn't the P-47 dominate post-war aviation? Because turbocharged piston fighters represent a thermodynamic ceiling. Jet engines eliminate the propeller efficiency limit. 10. Economic reality, mass production. Over 15,000 P-47s were built. That scale matters. Visual, wartime factory assembly lines. Manufacturing constraints shaped design decisions. Air-cooled radials simplified production. Rugged structure reduced maintenance complexity. Standardized parts improved throughput. In wartime, reliability beats perfection. An aircraft grounded for maintenance is useless. 11. Final verdict, was it insane? Yes. But not because it was flashy. Because it embraced engineering compromise. It accepted higher weight, higher drag, complex ducting, massive internal volume, in exchange for high-altitude power, survivability, structural robustness, devastating firepower. The P-47 Thunderbolt represents a specific moment in aviation history, the absolute peak of piston engine, turbo-supercharged, high-altitude fighter design. It was not elegant. It was not lightweight. It was a flying thermodynamic system wrapped in aluminum. Closing thought. Engineering is not about beauty. It's about constraint management. The laws of thermodynamics do not negotiate. Air density does not care about strategy. Drag does not yield to patriotism. And yet, through ducting, turbines, alloys, and sheer industrial scale, engineers built a machine that bent those constraints just enough to win. The Republic P-47 Thunderbolt wasn't insane because it defied physics. It was insane because it respected physics and exploited every loophole available. That's the real engineering story. And that's what makes it extraordinary.